bound. I just want to do one more example, which is the more general exponential family. So suppose you have IID data from an exponential family in canonical form of this form. And then you write down, so this is basically the, in our previous notation, this would be the density of a single observation. And then I have the density of, joint density of n observations. This factorizes, and you take the log, you simplify. We've done this multiple times before. This is the expression that you get. And so if I want to do the Fisher information calculation, we can use the alternative expression in terms of the Hessian. So I take derivative twice. The first term is linear, so it goes away. And I get negative n times the second derivative for the Hessian of it. Okay, and so the negative of it would be n times the Hessian, and it's deterministic. So the expectation would also be solved. So it turns out that like the Fisher information is going to be n times the Hessian. And it turns out that this is also equal to n times the covariance of T if you will. And this equality basically is a form of statement of attainment of the Kramer-Rao bound. To see it, let's just think about the single like observation case n equal 1. Then we know that mu of theta is expectation of, let's say mu theta is the new parameter, the expectation of theta is the derivative of the first derivative of a theta, right? And so the Kramer-Rao bound in this case would be for estimating this mean parameter. I suppose I want to estimate the mean parameter. That's my g theta. So you get mu prime theta squared divided by I theta. So mu prime would be the derivative of this, which is the second derivative of a squared. And then the shear information from the above is just n is 1 here. So because it's going to be the second derivative of a theta. So it simplifies to a double prime theta. And this is really the variance of theta. Sorry, the variance of t. And so this is saying the Kramer-Rao bound says the variance of delta is bigger than or equal to this for any unbiased estimator of t. Sorry, mu theta. Okay, so any unbiased estimator delta of mu t, so call it delta. The variance of this quantity is the variance of t, and t is also an unbiased estimator. So this shows that t is the u of u, and the Kramer-Rao bound is a t. Something we already knew. But so there, this is under regularity assumptions that allows you to go through the Kramer-Rao argument, the intention, derivative, expectation, and so in those cases, yeah. So the more general case, yes, I think you could do it, you figure out the case for larger and you guys. Okay, so in exponential family, it doesn't tell you something new. And then there's this extra example, which you're going to skip if you want. You can go through it. It's an example where the Kramer-Rao bound is not a thing. And so you can compute the U of U, you can compute the CRV, and there's a difference. There's a gap. Okay, any questions about Kramer-Rao bound? If not, let's move on because you're a little bit behind. We've talked about this. We're going to see Fisher information later in the course. But I want to switch to the next topic, which is going back to this. Yeah.
So Christian EU does not have to attain CRV. The CRVs are always unique. this relationship.
No, CRV is a lower bound than the variance of any unbiased estimator, okay? And the variance of a UMVU is also a lower bound. Okay. So the variance of the UMVU is the smallest possible variance by definition, right? So what happens is that the Kramer-Rao bound could be strictly bigger. Sorry, strictly smaller than the UMVU. Okay, so this is the variance, the lower bound and the variance of any unbiased estimator. UMVU is another, like a particular unbiased estimator. So this is always going to be less than or equal to the variance of the UMVU, but there could be a gap. So it's like variance of delta is bigger than the variance of, let's say, UMVU. So bigger than or equal to CRV. So this inequality, this might be strict. Okay, and in some cases it's strict. So the attainment means this is equal. Yeah. Other? Yes.
Does that mean, for exponential family, it's always possible to attain the.
Almost always, assuming that you mean that there was this if you remember, there was this regularity, I can interchange the derivative and expectation. Right, and then given that this formula also holds, which we didn't talk about. There are two alternative formulas. So assuming that you can do that, exponential families, they can do that, yes. And there was like a statement here. If you want, you can go read this paper. The attainment is related to the exponential formula. The paper claims that CRV is attained only in exponential families, in a sense. Any other questions? So you're going to go back to the decision theory. And we talked about the issue that comparing the risks of estimators or the issue that arises when we try to compare the estimators based on their risk functions. So the functions are generally not comparable. So one estimator could be better than the other on a different part of the parameter space, whereas the other one could be like better on a different part of the parameter space. So one approach was to restrict the class of estimators so that we have this uniform domination, which is the idea of the UMVU, for example, by reducing or restricting to the class of unbiased estimators. This is another way. So there's another way is this reduce the risk to a number by taking either a maximum or a weighted average. And so I want to talk about that. So if you take a maximum risk and try to find an estimator that minimizes the maximum risk, that would lead to the idea of minimax estimation. If you take a weighted average of the risk, so you need to put a weight on the parameters, and this would lead to a Bayesian estimator or Bayesian approach, or at least a decision theoretic view of the Bayesian approach. So Bayesian statisticians may not care about decision theory, but you can view the Bayesian approach as a particular solution to the problem that we have, which is reducing the risk to a number by putting it like a weight on the space of parameters we'll call prior. So you need effectively what we do is we put the probability distribution, I think. So theta used to be for us a deterministic unknown quantity. That's usually how frequentists approach a statistical problem. So far, what we have been doing is that. So we have a parametric family of models, if you remember. So the basic ingredient of a decision theory framework is a parametric family. So these parameters are treated as unknown, but deterministic. And so what the model is saying is like, I observe an observation from p theta, but I don't know which theta. So in the Bayesian framework, you would think of this as a conditional distribution. So you'd say in the Bayesian, so this is like frequentist. The Bayesian view says, let's think of this as like there is a parameter which is random. And condition on this parameter being little theta, this is distributed like p theta. So this p theta is really the conditional distribution of theta. And then I can put a prior distribution on theta, which will denote with lambda. So once I do this, I have fully specified, so fully specified joint probability model for x and theta. So this is gonna have a well-defined joint distribution. And then I will connect back to the frequentist risk. But once I have this, then I could, let's say I had an estimator. Remember, the estimators are maps from or like estimation rule or decision rule maps from X to the parameter space. So delta applied to X is going to be a parameter estimate of the parameter. And then I have the true parameter, which is also going to be random in our setting. And then I can take the loss. And this is going to be random. And it's going to be random because of the joint randomness of theta X. And then I can take the expectation. And this would be what they call phase risk. So the relation with the original frequentist risk is Wire conditioning. So if I condition, for example, so I can say I can condition, remember the tower property. Suppose I condition on theta, right? This quantity, what is this quantity? This quantity is the frequentist risk evaluated at this random theta and delta. So the way to see it is by noting that like the expectation of L, let's say theta delta X, given theta is equal to theta, I can just replace this capital theta here with theta delta X, given theta equal theta. And so this thing only depends on, when I calculate this distribution of X, conditional on theta is what goes into calculating. Conditional distribution is given theta equal theta is just p theta. So this is really the same as frequentist way of writing things, right? So L of theta delta X, right? So what this notation is saying is evaluate this under the distribution X being the P sub theta. This is saying the same thing. So we identify sort of this distribution with the conditional distribution of X given theta. So this is the Bayesian view, this is the frequentist view. At this point, they're the same. But once you have this, this is just R theta and delta X. So this is deterministic. And then this might have slow theta or channel theta. So that gives you that. Okay, so in this fashion, this is just that, and you can see this is really an average. So I'm taking the average of the frequentist risk over the distribution of theta. Okay, another way of seeing it is this is also equal to, running out of space, integral R theta delta d lambda theta. Okay, this is the prior distribution, and this is really showing you that's really average of the well, this is the everything is in there, right? So this lambda is a measure, if you want, it's like lambda theta d theta. Okay, it has a like density respective of Lagrange. Right, measure theory of the page. write it like that, then it's really a weighted average, right? So you either start from frequentist risk, you take this average, and this has this meaning, or you want to start here. So that's the same. So this thing is called the Bayesian or Bayes risk. Okay, so there is this one number, which is you can take the expectation under 20% of the theta, which is the natural thing to do here, and has this alternative interpretation as the expectation of the frequentist risk, where you plug theta and average over all possible thetas with respect to the prime. So in the discrete case, so this, if things are discrete, it would be just r theta I delta and lambda I. So let's say let me do it just downstairs here. So suppose, for example, omega is theta 1 up to theta k. Then a general distribution on theta is specified by k numbers that sum to 1. So I can represent delta sort of equivalently as this vector, or lambda, let's say the density, with respect to the counting measure. Then that integral would be just summation lambda I r theta I delta, which is clearly showing you that things are averages. Okay. So this slide is going through that. So we do start from the primitive family, interpret the data as a conditional distribution to the data, together with the prior distribution. So now this marginal distribution that we put on theta is called prior. Together they define a joint distribution on theta and x. For frequentist risk, we interpret it as a conditional expectation, and then when I plug the theta in, I take the expectation using power property, I get this relation. Okay, so this is the other way around. So this is really the Bayes risk, which is also equal to that, and we call this or represent this in R lambda delta. So it depends on the prior, it depends on delta. But if I fix the prior, then it's really a number. Okay. Sounds good. Let me go back, see if any questions. This we have written as R lambda delta by definition. Is the setting clear? So the decision theoretic view of Bayesian approach is to try to minimize the Bayes risk rather than there were no risk. Okay. So I want an estimate that minimizes this one. Once I fix lambda. Sounds good. So that's Bayes optimal. So the estimator or the decision rule that minimizes this is called the Bayes rule. And it's the optimal rule under the Bayesian. Questions? It's either clear or completely unclear, which case. We can move on, see what happens. So the Bayes rule is okay, it's going to be with respect to prior. So once I fix the prior, if I minimize the stage risk, okay, the quantity that I had there. And so you can ignore this. This is, again, you can write it in terms of integrals, but you should be able to do that yourself. And I believe, yeah, right. So my notation, it might be a little bit, so this I might write as lambda theta, the density of the prior, or might write it as pi theta. So we'll see. I think probably pi theta. right? If I minimize the stages of delta, that's the Bayes rule, and there's a really easy, very easy solution. So there's a general solution. There's almost like a closed form. It's not closed form. We know what the Bayes rule is. But first, I'm gonna put the lambda here. So the Bayes rule, because it depends on the prior, we're gonna have lambda pi, which you do not doesn't really depend on the prior, and also depends on the loss. So this is the result, which is really nice. So assume that there exists an estimate or a decision rule that has finite Bayes risk. If there is no such thing, then you don't have to worry about Bayes rule. Okay, the second assumption is this quantity, posterior risk, can be minimized. So what is posterior risk? So if I look at the loss function, theta and then the action, conditional on x equal to x. So this quantity depends on the conditional distribution theta over x, which in the Bayesian math is called the posterior. Okay. This is another distribution of theta. So we have a distribution on theta, a priori, which is a prior, and then we have a distribution x given theta, and then combine, they give me the joint, which I can then invert in the sense using the Bayes rule, I get theta given x. So this is based on that distribution, theta given x, which is the central object in Bayesian statistics. So this posterior distribution, calculating this quantity, it looks like risk because it's an expectation of loss, but under this posterior, so that's like following posterior risk. So for any given x, I can minimize this, assume that there is a minimize. Okay, for almost mu almost mu is not a limit. Control everything. Arguing there is at least one limit for almost every x, then we call this delta lambda x because it will depend on x. Then it turns out that this is the Bayes rule. Okay. There are like formal ways of proving it, and there's an informal way, which I'm going to do the informal way, which is rather nice. So the informal way is like I want to minimize r delta lambda, which is integral of the expectation of L theta delta x. I can write it by double expectation, right? I like Tower property. I'm going to condition on x first, and then take an expectation outside. Okay. So condition on x first, and then I can write this as a like a an integral. Okay, so the outer expectation, so this is the Tower property. The outer expectation is really expectation. I'm going to write it like this: L theta delta x, conditional on x being little x, and then I'm going to write nu or d nu x, or okay, so d nu x is the marginal density. So this is the marginal distribution of x. Okay, so we had a joint distribution on x and theta. This joint distribution induces a marginal distribution called mu. It doesn't concern us, but this is average perspective. So this is going to be, the whole thing is going to be a random variable function of x. And I'm doing, if you want, okay, we can do maybe something else, like do p, to be more clear, px little x. So px is the marginal distribution. That might be more clear. So the key is that this marginal distribution doesn't depend on, it's not up to us. It's completely determined by the prior. I can't change that, but I can if I change delta, this is not going to change. What is going to change is this quantity inside, and this I can minimize at every point. So how do I minimize at every point? I'm going to choose this quantity. I can now replace this capital X with little x. You can also see here, this little x is valid because I'm conditioning on mixing capital X into the capital X, little x. This is because it's a quantity for every x. So I'm going to choose it to be the minimum possible value in all actions. Okay, so that exactly is this idea. Okay, so we pointwise minimize this point. So that the delta x that's going to be optimized for every x, choose an action here that minimizes this quantity over all x. That's that result. Okay, once we argue it this way, you can see why this is optimal. If you want to be formal, you just write things down and you say, okay, so once I do that, then conditional, this is conditional equality holds. Because by definition, delta lambda of x, so this is delta lambda of x, is the action that minimizes. So if I have another delta x, this is going to be conditional on x, this is going to be all of this and that, and then I need the expectation of both sides. So I'll leave that to you to argue it formally. Formally, it's just the definition applies this inequality and then you apply power property. But this is a little more clear. Okay, so we decompose the risk like that. This part is a weight that we can't control. This part we can control. We can control it for every x, which is delta x that minimizes it. Okay. Yes.
In the theorem definition, what is A again?
So every loss is a function of two variables. The parameter and an action. So this is just the bounding variable representing the second order. But what this is saying is I'm going to minimize the loss into second order, which you call it. But you can call it whatever you want. It's just the second argument is often reserved for the action. Yes.
So just to confirm, the R is the frequency loss. The R.
Which R?
in the
There's no R.
first side, the R.
This is this little r. Little r is the base risk.
Base.
Yes. Because I'm taking the expectation over the that's what I'm trying to do. So this expectation is we're expecting the joint distribution that there's no joint distribution in the frequency. And then I can expand like do this composition, conditional x first. Then the inner expectation depends on the posterior distribution as to take theta to x. And then the upper expectation is over the distribution. Yes.
So, delta of lambda is a risk minimizing estimator for fixed x. And the second question is, what do you mean by the last line in the theorem that lambda sub or delta of lambda is always?
Or maybe let's resolve the first question. So what is the first question?
So that's the delta is like a minimizer for a specific x, right? Like so it's some arbitrary like minimizer or like some arbitrary function that minimizes this.
So let's fix x. I'm gonna minimize this, I get a number. Okay. Change x to a different x, minimize this, I get a different number. So for every x you type in, you solve, you get a number. So this defines a function from x to these numbers. So that function is called delta lambda. Right? So we are solving an optimization problem for every little x. And potentially that optimization problem has multiple solutions, but let's say I take one for every x. Okay, that's, if I want to be a little bit more precise, this belongs to argument because this optimization problem has multiple solutions. For every x, I'm going to choose one solution. Okay, one action that minimizes this. And then that will define a function. So let's say x1 goes to some number, right? Which I'm going to call delta x1. X2 goes to some other number, which I'm going to call delta x2. And once you do this, you see that delta is the derivative function on this x. Okay. Does that
It's a very contrived definition.
It's not contracted, it's just definition of a function. The function, a function is like a map that maps some elements in the domain to another domain. The way that you map it is not important. Just how general it is. Right? You have to give me like a recipe. How do I map this x to a number? And once I have that recipe, it's a function. Okay, and so what was the second question?
I just understand then that delta sub lambda is a base rule is the.
What is not, so this is gonna be a function on the space of X, right? So this goes from the way that we define it, takes the anything in the space X and maps it to actions. So that's by definition a rule, decision rule. And so it's a table that minimizes this. Why there's an A, maybe that's the thing, because if this minimization is not unique, then I can choose different solutions for different X's. But for a particular X, you can be some multiple arguments, and any one of them would work. And so I get potentially different phase, right? Phase rules could be multiple. But again, under some conditions, specifically, I believe, we'll talk about that. There are other conditions this phase rule will be unique, so there would be a unique minimize. So I'm going to give you some formal statement. But in general, the base rule might not be unique. Okay. Questions? Yes.
So in the delta in some case, you mean posterior risk is equal to?
No, base rule means it minimizes the base risk. Among all decision rules, it's the one that has the smallest base risk. Estimator. Estimators and rules are sort of kind of like synonymous like for us. If you do estimator, is it better? Does it look better?
Yeah, because when I first saw base rule, I thought that the base rule.
Oh, you mean the base?
Like,
Okay, yeah, okay. It's not the base rule and probability. Okay. Good point. So I'm gonna use estimator. I should edit this. We're gonna use base rule later to calculate the posterior, but this is base decision rule. Okay, so that was a decision rule. I never noticed this conflict potential conflict. Base decision rule. Good. Fine. Any other questions? AKA estimator. So base estimator is the one that minimizes. We're looking at like estimator for decision rules. The one that minimizes this risk is called the base decision rule or estimator. That's it. So let me show you the example. So first, we go back to the base rule. So the way to calculate that posterior risk is often via the posterior rule and calculate. So all reduces to posterior calculation in Bayesian analysis. So I need to calculate this quantity, and so this depends on the conditional distribution of x given, theta given x. And this distribution theta given x is called posterior. And the way that we can find the posterior now using phi. So phi theta is the prior, and here is all this like joint divided by this, I'm going to use the marginal like m of x. So the marginal, which we're going to see, this is the integral above, or all through there. And so this is the ratio. Okay, the density, the lower density. So the density of, so this is like base rule for densities. So you can get the density of posterior by multiplying this quantity, which is now viewed as a likelihood because we're viewing this function of theta and the prime, and then divide by that. But because I just care about the form of this as a function of theta, often people know it proportional to the likelihood times the prime. Because all this is doing is normalizing factor, so normalizing cost. So I have to compute it by hand, but this, if I write it like that, there is no loss of information because I know that this is the density has to integrate to one. I'm just going to integrate this, whatever constant this is, I'm going to divide by it, which I'm just going to exactly. It's common to write it like this and then figure out the constant by alternative means. Very rare to integrate yourself. Either it's a non-distribution, this works most often is, or you actually care about sampling from this posterior. In which case, most methods that sample from posterior like this, we care about just this quantity up to the constant. You don't need normalizing constant. So you can do MCMC, give sampling. And none of this requires you to calculate the constants. Which is very good because in general, this normalization might not be feasible. Another point is that this density is equal to the same measure with its prior incidence. So for example, if you put a prior with respect to the Lebesgue measure, then the posterior would be density with respect to the Lebesgue measure. So the short, posterior is proportional to prior times the likelihood. That's like the central dogma of Bayesian statistics. So that's the only thing you need to know. And then you're a Bayesian statistic. And maybe a little bit of MCMC. So given that, so we'll see examples of this, but let's do a more general case first. So I'm not going to worry about the particular posterior. So I want to see what happens if I use, for example, quadratic loss here. So if L is the quadratic loss, so suppose L is example is the quadratic loss. And it could be like L, like it will be like G theta minus A squared if I want to estimate function of the function of theta. Okay, so that's my loss. Then the posterior would be just G theta minus A squared given X is equal to X. So minimize over A. So what do I get if I minimize this? Multiply out. Yes, so you get A squared minus 2A times this plus that squared. And then expectation is linear. So once you do that, once the dust settles, what do you get? So you get the quadratic equation in A. And it's safe to say that we can take the derivatives that equal to 0. And that would be the minimum because, yeah. So what would happen if you do it? I'm going to assume that most people know how to do this. I mean, if you do it in your head or on the paper, let me know what the answer is. Expand, take the expectation, differentiate, set equal to 0. What is the optimal A? Expectation of G theta over 2.
Or is just the expectation to at G data given S equals S.
Okay, now you're. You can't get rid of the conditioning. So it's the conditional expectation of g theta given x is equal to x. So let's say g theta is theta. Then this is just gonna be expectation of theta given x. So we arrive at the very simple idea that the base rule in the case of it's simple case under the quadratic law is just the conditional mean. Okay, the conditional mean of the posterior. So you calculate the posterior, you form the conditional mean. That's your base rule. Okay. Conditional mean of the posterior. I'm sorry. Posterior mean to the posterior. Special case. In the special case. Special case. Case. G theta equals theta. That's this posterior mean. Okay. So there's none of the posterior mean. This if you replace it with L1 loss, you know, data, then you get the median, posterior median. And in this case, it will not be. Posterior, yeah. But in any case, so once you change the loss, it's like a different feature of the posterior that comes out as the base rule. Okay, so the posterior is a distribution dependent on x. So it's a whole distribution. You can think of the posterior as mapping x to distributions. And then the base rule is like a base estimator is going to take a feature of that distribution. For every x, you pick like maybe the mean, the posterior mean. That will give you the base rule on the quadratic. If you take the median, you get the posterior, what the base rule under the L1 loss. So, okay. Sorry, yes.
Can you scroll up to slide 5?
5, okay.
One above it. Oh, okay, I didn't remember there being a condition on X, so I got confused.
Yes, yeah, so this is key.
Yeah,
Right, so everything depends on it. You're gonna use the data otherwise.
if you were to get like another round of new data, would your posterior just become like the entire?
That's a great point. So oftentimes in these problems, we have like fixed setting, right? But yes, in practice, what happens is you start with a prior, you gather some data, you get a posterior and theta, and if you're wise, then use this as your future prior data. You don't have to, but let's say I get more data. Now I have that this estimate of data. I can use the prior data, new posterior. And if things are IID, this procedure should, I mean, you can convince yourself that this procedure is the same as if I started with the prior and just used all the data. So it should hopefully work out, right? But yeah, but that's the natural thing to do. And that's believed to be like how we do. We believe that the Bayesian approach is our decision. We do decision making based on Bayes rule, then that's how you do. So you start from like a very vague or diffuse prior. You gather data and then you compute the posterior. Your posterior is going to be sharper. So the idea is usually you have a very diffuse prior and theta. You get some data x1 up to x, and oftentimes when you sample, then this prior might sort of like peak around a certain point, and then you get more and more samples. This might end up being, if things are consistent, you like start seeing a bigger peak. So, okay. In practice, probably data are not going to be IID, so you start seeing drifts and stuff like that. Assuming that everything is IID, eventually what happens is that this posterior is gonna, so you start from like a very diffuse prior, let's say, and your sample sort of what you, the first like n samples give you, for example, something like this. If you like gather more samples, you would get something like that, and so on. It's actually going to be not necessarily like there's going to be some, it's not like they all have the same center. But the center is like most Bayesian procedures are going to be biased, but eventually the bias goes away. We'll see. Yeah, my drawing is not good. So let's say, okay, let's do a simple case, like a little bit more concentrated. So you gather more data, the posterior become a little more concentrated, and the mean hopefully closer to the truth. More and more data, you would get maybe more concentrated and shifts better. More and more you'd get, it's like maybe the true parameter maybe is here. Okay, start shifting and concentrating. So that's what you'd hope to happen. Okay, the posterior often concentrates. And one way of analyzing, so this is not what Bayesian statisticians would do, but the frequentist statisticians, when they view the Bayesian approach, they would say, okay, they can't help like with assuming that the theta is constant. So if you see like Bayesian analysis, the frequentist analysis of Bayesian procedures, they assume that you have a true theta star. The data is coming from that, but I'm going to use the Bayesian machinery. Then they would show that as the sample size grows, this posterior is going to converge the theta star. So this is called posterior concentration. So you get the probability that this theta belongs to, let's say, theta star minus epsilon and theta star plus epsilon is going to converge to, okay, given x1 up to xn is going to converge to 1 as n goes to infinity. So something like that, okay? This is also random. So let's say almost surely converges to 1. It says posterior concentration. Was there a question?
So like if there's some kind of distribution shift, like in a millisecond sense over time through data, then like the Bayesian methods would maybe be able to like more gracefully handle that.
These are all great questions. I can't say for sure,
Yeah.
but potentially I would say yes, maybe, because at least the thing is there is a balance. So there is a balance between the prior and the likelihood. So even if your prior is wrong, once you gather more and more data, the effect of the we'll see the effect of prior is gonna like hopefully vanish. And so yeah, so I would say maybe that is going to be the case. But the issue is like when you have this distribution shift, it's reflected in the likelihood. Okay, so it's not maybe accurate. Maybe I should correct it. So if you use the same likelihood, the likelihood is incorrect, then you're not gonna be able to like handle. But if you somehow your likelihood is fairly generic, then yes, and you might be able to. Yeah, it's tricky. Because in the end, you compute the posterior based on the likelihood and the prior. It's not too sensitive to prior, but the likelihood. So the likelihood remains correct. Any other questions? Okay, so
So for this, where we have this base as basis,
what was that?
like, what are we, what's that, what are we?
You're proving that this is the Bayes estimation. The minimizer of the posterior risk is the Bayes estimate. So for example, under quadratic laws,
Like that's not how we.
no, we define the Bayes estimate as minimizers of the Bayes risk, not the posterior. So it's a Bayes, like this you have to give me an entire function. So give me a function that minimizes this Bayes risk. Okay, so this gives you a recipe how to do it. So for conditioning on x, I think the value for a is a number, let's define that particular amount. So this is saying that if we minimize this, doesn't tell you much. This gives you a recipe to actually calculate. right?
But just looking at that. It's really. It's really hard to tell whether this is, base risk or just free risk.
It is Bayes risk because first I'm writing theta as standard exactly. I'm calling theta here. So it's like, this is like the single interpretation is like there is a single distribution. Under Bayesian mode, there's a joint distribution. There's no longer if you look at the family, we don't have to worry about the family. Okay, it's just buried in the joint distribution. The family of the solutions we're looking at is such as conditional distributions of x to n theta. And I have a distribution of theta, now I have a full distribution of x and theta. Expectation is simply the joint distribution. With respect to the joint distribution of theta and x. Okay. Sounds good. Great.
So what's the?
Big theta is random, small theta is non-random. Any other questions? So let's do an example, see like this concentration. So consider x to be binomial, the parameter n and theta. This you can think of as the number of heads in a like a Bernoulli trial. And you want to estimate theta. So you write down the probability mass function for x. So that would be this hopefully well-known formula for the binomial probability mass function. And we put a beta prior. So the distribution of theta would be beta a priori, which has two hyperparameters alpha and beta, and this is the density with respect to the Lebesgue measure. And it's proportional to theta to the alpha minus 1 times 1 minus theta to beta minus 1. Why did we pick this? First, it's like a general parametric family for things that are supported on 0, 1. So theta is a probability, and so theta is the distribution of 0, 1. But the second is this particular form. If you look at this, it's very quite similar to the form of the likelihood. So the likelihood is viewing this as function of theta. So it's going to be proportional to theta to the x times 1 minus theta to n minus x. So this particular form is, as Bayesians would say, conjugate. So this is conjugate to the binomial family. It's prior is conjugate. What it means is that once I calculate the posterior, my posterior would not be this term. It's going to be still beta. Why? Because the posterior is going to be proportional to the likelihood times prior. If you do the multiplication, we can ignore this and choose x because that's a constant. So I get theta to the x times theta to the alpha minus 1. So I get theta to the x plus alpha minus 1. And I have 1 minus theta to the n minus x, the likelihood, and 1 minus theta to the beta minus 1 in the prior. So the exponents are added up. And so I get 1 minus theta to the n minus x plus beta minus 1. And this is, again, the density proportional up to a constant to the density of a beta distribution with now this new parameter, like new alpha and new beta. So it's really, you can say the posterior distribution of theta given x is a beta distribution with parameter alpha plus x and n minus x plus beta. And I didn't need to calculate the horrible looking sort of normalizing parameter. Another concept of normalized. Whatever normalizes the beta distribution. Okay, so this helps. So this conjugacy again means I started from beta prior because of this particular likelihood I remain the beta family for the posterior. So the posterior is the same family, and so for this reason, at least traditionally, conjugate priors are very favored because it's easy to calculate. So you have to, I mean, people will say you have to like, prior has to like, there are different considerations. Technically, you shouldn't worry too much about computation, whatever the prior belief is the prior. But in practice, you start from some time, you decode your belief in alpha and beta. That's for simplicity. Okay, so whatever I believe a priori I have. So for example, the expectation of this prior would be alpha or alpha plus beta. So if I have a guess of what theta has to be, let's say 1/2, I'm gonna set alpha or alpha plus beta to be 1/2. And then maybe some uncertainty, I have uncertainty of say plus minus 0.1. And then I set the variance to account for that, and then that gives me alpha and beta. So that's it's very hard for people to like have a complete prior distribution. There's this literature on prior elicitation. So if you have an expert how to elicit a prior, and I just learned about this, that there is this literature, but usually people don't care. Nowadays, maybe you care. So if I read that paper, I'll let you know, maybe, or you can read. But oftentimes you would not elicit a prior, just have like whatever is convenient, and then maybe like set up this hyper prior, like hyperparameters. So in any case, so that's the posterior. And for example, if we have the quadratic loss, and if you want to minimize the Bayes risk, then we know that the Bayes rule or the Bayes estimator is going to be the expectation of the posterior, right? So the expectation of a beta distribution is just, again, the first parameter divided by so on. So you get alpha divided by n plus alpha plus beta. So very easily calculated Bayes rule. So this is the optimal, basically, Bayesian approach. Okay, if you're working with quadratic loss. So that's going to be our estimate. Good. Probably get the point coming with heads. Yeah. And then you can rewrite it in a nice fashion. I can rewrite it as 1 minus alpha. So just to remind you, this is just so if you have a theta which is beta distributed, parameters alpha and beta, then the expectation of theta is alpha plus beta. And so the prior expectation is this, the posterior expectation would be this plus that. And so that's the posterior expectation. You can see it's involving, like it involves x, which is what we want. And then I can rewrite it in this fashion. It's just some algebra with this alpha. And this lambda is something between 0 and 1. And the nice thing about this is that this is writing the Bayes rule as a convex combination of x over n and the prior mean. Okay, so it's like interpolating between the prior mean and x over n. So what is x over n? The MLE or the UMVU or like the natural estimator is x over n, right? It has all those nice properties, unbiased, it's minimum variance, uniform minimum variance unbiased, and also MLE if you want. And so the Bayes rule is actually like trading off between that and the prior. So if you tell it like a prior is here, it's going to put some weight on it. But eventually you can see this quantity is going to go to, what happens to it if n goes to infinity? This goes to 0, so that's the beta of the prior goes to 0 the beta. So this is like completely beta derivative. At least tells you like, so there is going to be a bit of bias. So this is going to be biased. Right? Because it's unbiased, extra term is going to be biased, but the bias is going to go over. The Bayesian approaches often have bias because of the prior. But asymptotically sort of unbiased. And then you can also calculate the variance of the posterior. And the formula is a little more complicated, but like alpha times alpha divided by something. But then the variance is going to be like 1 over n, the order of 1 over n. And you can see the posterior really concentrates. So the prior variance doesn't have anything to do with n, so it depends on alpha and beta. But the posterior variance is gonna be like proportional to 1/n. So you really have this situation. It's really this picture that I draw here. Yeah, so let's say, so you both like move a little bit because the lambda is going to 0 and also concentrate because the variance is going to 0. Eventually, hopefully you get, and then x over n is also sort of convergent, hopefully, and there as well. You know, the x over n converges to theta star because of the law of large number. So what will happen as n goes to infinity is this rate goes down, this rate goes to 1, x over n is also moving towards the right direction. So you're going to be consistent. And the variance sort of shrinks. Sure, your uncertainty goes down. So one of the reasons people like care about Bayesian approaches is sort of this gives you like a measure of uncertainty because this distribution, it has a variance, you can have confidence bounds, and so you don't necessarily just get one point estimate, you get like uncertainty quantification for free in a sense. Assuming that you believe the prior is correct and all that sort of stuff. Questions? So this like very simple example captures all the things that you might want to care about in Bayesian approaches, except for the fact that in some cases you can't write down the class A and you have to resort to numerical methods. So, but except that, this sort of nicely encapsulates a lot of interesting things that are going on. Yes.
I apologize if you went over this, but like, why did we choose a beta prior? Is it just because we wanted to?
Right, as I mentioned that. So anyone conjugate. So yes, basically because of the simplicity. So once you pick that, interacts with the likelihood, it gives you something which is again beta. If you choose a different form, then the density would not have like necessarily a nice form. It's still okay, but you have to take the integral, for example, and calculate the mean and the variance. The basic idea is convenience. The convenience. Yes.
This conjugacy just mean the posterior that's the same distribution.
Is within the same family, yes. Not the same distribution, but like within the same. Other questions? Yes.
You mentioned it's important to get for mean. Like, so when we are assuming prior, for example, is it also super important to get down exactly what A and betas are, or just prior mean? If we get a prior mean, that's sufficient.
No, what I was mentioning is the way that you set up the prior, so there's these hyperparameters, you have to decide, right? So you can decide the entire prior. What I was saying is that it's hard to come up with this entire prior. You often like traditional people assume that the nice prior to form. Now there's just two parameters that they have to decide. And the nice thing to decide is, for example, in this case, alpha divided by alpha plus beta is the mean of the prior, so you can have like an opinion about the mean. So if I, for example, if I think the coin is fair, it's natural to set alpha over alpha plus beta is 1. You don't have to do it, but you have to somehow figure out alpha and beta, and this is one way. Right, right. There's another way that Bayesians deal with hyperparameters. Anyone knows what the other approach is?
So, or
You put another prior on these, and then they would have hyperparameters. What do we do with those hyperparameters? With more prior. Prior to top priors, so you get the hierarchical Bayesian models. And at some point, you're happy to say, okay, I don't care about these hyperparameters anymore. I just said it. They're not going to be affecting as much. Yeah, but that's generally the approach. It sounds funny, but it works. So it's especially, for example, this case is like that. So if you have a Gaussian family, this is the same setting. Xi is a normal, not the same setting, but similar to the exponential family. So theta and sigma squared. And then I put a Gaussian prior theta. In this case, I'm assuming sigma squared is known. If I don't know sigma squared, I put a prior on sigma squared as well. And then I can put a prior on the prior. So it's low. So now, sigma squared is wrong, theta is unknowns or location patterns. So it's not going to take that, having a that, connect with the Gaussian prior, and it turns out that this is conjugate. There are different ways of seeing it, so you can start writing down the likelihood, which is the density of this, and then like, the density of that, multiply, and then do algebra to see that the result should be Gaussian because this would be exponential of negative some quadratic in theta, and this is exponential of negative some other quadratic. The product would be exponential of the negative, the sum of two quadratics, which is another quadratic. So it should be Gaussian. Yes.
My example above showing equal data.
Can I say that again?
The example above showing the equal data,
Yes.
then it tries to apply it on the next side. How we're going to do combination this way.
Yes.
I thought it's about that. Yeah.
Right. So you're talking about this.
Yeah.
Yeah. Right. So, what you pointed out at the end is true. So as long as your prior has proper support, then it really doesn't matter as it goes to infinity. If I put the prior wrong, so let's say the true, let's say theta, there is a theta star. Again, Bayesian's, this is not Bayesian view because there is no true theta star, theta random. But let's say there is a true theta star 0.9, and I pick a prior, which is it's like maybe uniform 0 to 0.7. So I can put a uniform prior, right? So uniform prior on this interval and then 0 elsewhere. Okay, so this doesn't have support. And so this is not gonna, in this case, we're gonna have a problem. The posterior is gonna go like concentrate around this. It's this barrier generally. So you can have like asymptotic bias. But if your prior puts enough, like at least there's mass on the neighborhood of the true parameter, then you're gonna be fine. Hopefully, yes.
That's the answer.
The uncertainty quantification comes from the variance posterior. Right, so this is mean, there's a variance. And so it determines how peaked you are around the mean.
So they might have the answer.
It's gonna shrink, yes. Yes, I'm not showing the variance. I think I show the variance in the next example. So let's do the next example. You'll see where the variance comes in. Yeah, let's do this. So in this case, the Gaussian prior leads to a Gaussian posterior. One way, as I mentioned, is to just write down the likelihood and the prior, multiply, and then look at the form. It's exponential to negative some quadratic. That should be Gaussian. The other way is like using the properties of Gaussian distribution to write this as, this is really saying, I can, conditional on theta, I can write xi as theta plus some noise. Okay, so really, if you think about this, xi can be written as random theta plus wi, where theta is like independent of wi. Then if I condition on theta, this is going to be fixed and this is going to be normal. So assuming that wi's are normal, zero mean. And variance sigma squared, and they're independent. So theta is independent of wi. If you give it some thought, you'd see that this representation is equivalent to say with this. So if I do that representation, then it might be easier to understand that like what the posterior has to be, because now the joint distribution is going to be, if I look at the joint distribution of theta and x1 up to xn, the joint distribution is a linear transformation of theta and wi. So theta w1 up to wn, by linear transformation goes to theta x1 up to xn. And these are at this stage where everything is independent. So theta is independent. W1 to wn. So independent normal variables lead to a joint Gaussian distribution, and there's a linear map. Whatever you want to call it, let's say A. So under linear mapping, Gaussian distributions really like are preserved, so this is going to be multivariate Gaussian. And because it's multivariate Gaussian, we can calculate, for example, the mean turns out to be zero, and the covariance matrix, that's gonna be there. Okay. And there are rules for calculating that, so you know. So this is like 0, and there's gonna be covariance matrix that you can calculate from the properties of the A, and then once you have this, you can, there are known formulas for conditional distribution of one part of a Gaussian vector given the other part. So here we want conditional distribution of this part given the rest, and just look up Wikipedia and remember this. It's just normal with the formula for the mean and the formula for the covariance, which you can read from this covariance. And so once you do that, we're out of time. So it turns out it's Gaussian with a certain mean and a certain variance, and the mean has again that decomposition. The convex combination of the sample mean and the prior mean, and then the variance has, this is like precision, therefore the variance has a nice form. So you can see the precision goes like linearly up with the variance string. And then this is like again differential, right? So the same situation happens here. Okay, I think we're out of time. Any questions? Yes. Okay. Okay. Thank you guys. See you next time.